Welcome back. So, in this lecture we are going to talk about levels of digitization in multi-loop feedback control in switch mode power converter. And when you talk about multi-mode control, so in general I know the current mode controls is a good example of multi-mode control, multi-loop control. So, you want to recapitulate analog current mode control, then we will start discussing what are the technique for digitizing multi-loop feedback control, which is a current mode control. Then we will talk about sampling and quantization and summary of multi-loop digital control, and then some aspect of performance and cost trade-off. So, if we go for peak current mode control in a buck converter, and this is the diagram of the buck converter, and here we are using a current sense resistor here, and then there will be a current sense amplifier, and this sense current is a feedback for the loop. So, this is a peak current mode control architecture, and here it is the feedback voltage which is actually tapped across a resistive divider, and then we are also using a fixed frequency clock, external clock, and this is a sense inductor current. Now, if we go inside the peak current mode controller, what is there? We know that first the reference voltage will be compared with the feedback voltage, then it will generate the error voltage, then there is a compensator which is a voltage controller. Then output of the voltage controller we generally call as a peak current reference, or it is a voltage reference, because we are using a sense voltage which is actually capturing the current inductor current waveform, and then it is compared, and their output of the comparator is goes to the latch circuit. This is a latch circuit. Okay. Now, in this control we have two loops. One is the voltage loop. So, this is our voltage loop. Okay. And this is our inner current loop, because it is a sense inductor current. So, it is a inner current loop, and in current mode control it is well known that outer voltage loop ripple, that means if we talk about the output voltage ripple, we generally consider 1 to 2% of the Vref or even less. But when you consider the inductor current ripple, then we generally consider 20 to 30% or even higher of that IL average, that nominal value. Okay, that means the nominal value is basically the nominal load current for a buck converter. So, if we are talking about a 20 ampere nominal current, so 30% of 20 ampere means it will be 6 ampere. So, it can be 4 to 6 ampere is the current ripple. So, we can imagine the ripple in the inductor current actually is quite significant in terms of their percentage compared to that in a voltage mode control, because in voltage ripple, because we generally want to achieve a clean output voltage, although it is not achievable, but still we want to achieve the average value, the ripple should be very low, but the current ripple is large. So, generally the current dynamics are much faster and the voltage dynamics is slower. So, now the question is, in this two loop control, how to start digitizing, keeping in mind that voltage ripple is much lower and the current ripple is much higher. So, what is the mechanism for sampling? So, if you take the overall current mode architecture, so this is the inner current loop that we have discussed, and this is the outer voltage loop, right. So, and this is the inner current loop. So, that is why it is a good example of two loop control. Sometimes we call it as a cascade control, master slave control. So, inductor current loop is much faster and it has around 20 to 30% ripple, whereas it is just 1 to 2% ripple of this with respect to Vref. Now, the question is how to start digitizing this loop. That means we need to retain the fast dynamics of the inductor current, but voltage loop dynamics, although the ripple is smaller, if we go for small signal based design, then generally the voltage loop bandwidth is lower. That means we generally consider around 1/10 of the switching frequency. So, the compared to the current loop, and current loop generally we use almost full bandwidth, or the bandwidth of the current loop is decided by the current sensor. That means, if we use a current sensor which has like a 10 times of the switching frequency, so the current loop bandwidth will be decided. but the voltage loop bandwidth is lower. So, now we have to pose the question, how to start digitizing, where the outer loop bandwidth, if we talk about small signal model, is lower, but the inner loop bandwidth is faster. So, one architecture, the high bandwidth current loop, which has a large ripple, let it be in the analog domain, because this will carry a significant ripple information and which we cannot compromise, and also the current dynamics is much faster than the voltage dynamics, because we have discussed about the percentage ripple. But generally for the output voltage we have a large capacitor, because that is a standard process of any POL regulator, where we take the inductor to be much smaller, and if we talk about 1 megahertz switching frequency, the inductor can be in the range of around 200 to 500 nanohenry, whereas the capacitor, depending upon your input output voltage, undershoot and overshoot requirement, it can be as large as several hundreds of microfarad. So, you can imagine that voltage loop dynamics is much slower. So, it is reasonable to keep the voltage dynamics in the digital part. That is why we are putting A to D converter, that is digitizing. But the next question, when you have this digital voltage, then reference will be digital, error is also digital, and controller is digital, and we have discussed in the previous lecture that digitizing the single feedback loop. There, after digitizing the voltage, everything else was digital, we had to only consider the sawtooth waveform inside, which is also digital. But here it is a mixed domain, that means you have voltage in digital after the ADC, compensator is also digital, but the output of the compensator, which is generally used for the current reference, but the inductor current is analog domain. So, naturally you need to consider a D to A converter. So, that means when you take this architecture, you have one ADC, it is called mixed signal current mode control. This is a version of digital current mode control, where we use a mixed domain, that means analog loop for the current and digital loop for the voltage. So, current feedback in analog domain and voltage loop in digital domain. Now, you may ask, one of the challenge here is that you need ADC and DAC. So, the cost of the DAC can be high, power consumption can be high, but it retains the fast dynamics of the current. Here also it is another thing we have to keep in mind, this is an analog comparator. So, we cannot have a very fast comparator, because if you use a fast comparator, then it may consume more power, that is another issue. Another issue, that since we are sensing the inductor current, then there can be noise in the current, particularly switching noise, that means when switch turn on turn off, there will be some spike, and this is compared with the digital, the analog version of the digital signal, where it will be constant if you take one sample per cycle. So, it will be, because we have discussed in the previous lecture, if we take one sample per cycle where there can be delay, then the voltage loop will be updated once in a switching clock or switching period, and that means for the throughout the switching period it will be constant, and then the controller will also be computed in synchronism with the clock. So, that means the controller output will also be constant for the whole cycle. Now, once you have the DAC output, it will be also more or less constant for the cycle, but this inductor current actually when it touch, that means peak current mode control, there can be spike. So, then you need to sync, that means you need to use the trailing edge modulator that will actually avoid any fast multiple switching. So, that means there is a modulator, and this is pretty standard. But the question is, in this architecture, you need a high speed analog comparator, current sensor is analog, so but it can retain fast dynamics. But the question is, then why to put digital controller? Why not you put all analog, because anyway current is analog. So, the question is, this digital controller can be tuned, because you need to update the controller value. Suppose if you are talking about a PI controller, so if we use the same value of PI controller for the entire operating range, then we have discussed in our earlier course, that means the design of compensator we have carried out based on pole zero cancellation, or there can be conservative approach, but if we use a fixed gain comparator, then this will be designed based on the worst case, but the converter will not operate worst case majority of the time. So then we will lose performance. That is one aspect. The second aspect, that means we should update the controller value, and we can use a lookup table to update the parameter, and by using some information either load or input indirectly. That means we need to use some information of the load or the transient, and that can be captured by means of ADC bit. That means how it is updating. That is one possibility. Another possibility we will discuss, if you go for large signal transient. In fact, we have discussed large signal tuning. We can in fact actually update this controller value in such a way we can get fastest transient. There we want to retain the ripple information of the output voltage. Okay, that means we need to emulate, or we will discuss some aspect there. So we can achieve almost fastest response like a time optimal control, but due to the delay of the ADC, the performance may be limited. That is another possibility. The third possibility, since we are generating the reference current from inside of the digital controller, that means this whole in digital, we can always use a programmable current reference, because in peak current mode control we should be able to protect the circuit. That means if you want to protect, we want to program the current reference either higher or lower value, because if we use a program current value from the digital domain, then it will limit the actual inductor current. So you can actually keep the actual limit inductor current by using an external command. That means you want to command that I want to limit the current for 4 ampere or 10 ampere or 15 ampere. So this is much flexible by just a command line, because this is ultimately a number which you can adjust through a register. Another aspect, even if you are going for large signal transient, because of the delay you may lose the control loop bandwidth, because we have discussed the digital control has some shortcomings. When you have this A to D converter, we cannot have a very high sampling rate, because that will unnecessarily increase the cost and the power. So we have a limit on the ADC conversion rate, and that because of the limit we will have a delay. But imagine if we take, let us say for example, an analog comparator, and if you look at how voltage loop is deviating within some hysteresis band, then you can quickly ramp up this current by means of some nonlinear algorithm. That means you can increase the current very rapidly, then we can bypass the linear control loop. So all these possibilities are there. Or if you go for, let us say if you are talking about PFM control under light load, because we have discussed and we will be discussing in this course, and even we want to implement, if you are going for peak current mode pulse frequency control, which will actually increase the light load efficiency. So we can, there we need a constant current difference, and then on time will be automatically adjusted, that it will behave like a constant on time control, and this will also ensure that voltage ripple will not go beyond that, because we have discussed in lecture number 24 in our earlier course the different light load control method. So here we can set the current difference to optimize the efficiency under light load control. So there are many possibilities exist which will not be possible, or in fact it will be very difficult in analog control. So that is why this loop enables to do whatever you want other than just simply tuning the gain. Another architecture, we can keep even the current loop in digital. So earlier we will retain the voltage loop and we discuss about various possibility. Now we keep current loop also in digital, but we have discussed the current has a large ripple which is 20 to 30%. So we cannot simply take one sample per cycle, because then you cannot get an on-off operation for the whole cycle. If you take only one value of the current and one value of the voltage, then the current reference will be fixed for the same duration. Sample inductor current which is here, sample, that will also be fixed. So either the current difference can be above sample value of the current, then the whole cycle will be on, or the current sample can be above the current difference, then the whole cycle will be off. So you cannot get an on-off operation, either will be fully on or fully off. So eventually it will lead to a lot of nonlinear phenomena. So in order to avoid that, you need to add more higher sampling rate for the current, so that you can retain some useful ripple information, and that also is difficult if you just take 4 sample or 5 sample. That will not only increase the ADC sampling rate, but that may also lead to a lot of nonlinear phenomena. Okay. So that is why we may not, this technique has some limit because you cannot have a very high sampling rate of the current loop, because that will unnecessarily increase the cost. So, this is called fully digital current mode control with high current sampling rate. Here the current and voltage both loops are digital. So, everything is in digital. Then how to address this problem? One way to address this problem, we take one sample of the ADC. That means, as if these two ADC will be a time multiplex. You use a time multiplex. Time multiplex, that means it can be a pipeline ADC. Pipeline ADC, where we can mux the analog channel and we can take the sample voltage and current at two different time instants. Once you do that, that means you are taking the current, suppose for example, this is my inductor current and we will be discussing this, and suppose you capture this inductor current waveform. So, then you can interpolate by means of a sawtooth waveform. That means this can be sawtooth waveform internally. That means, so this block will be a ripple emulator. So, there will be additional block which has to be a ripple emulator. Actually, this ripple emulator job is done by this guy. It is not needed because it is taken care by this sawtooth, because either you add the ripple with the current sample or you subtract the ripple from the current reference. So, they will be analogous. So, that means here as if we are taking the ripple current through this a virtual ramp. That means this ramp is as if trying to provide the ripple information of the current which is lost because you are taking only one sample. Now, there are many research papers, that means many people try to get the actual slope. So, that means the slope of this ramp people try to achieve identical to the inductor slope. And how to do that? Naturally, you need to know the information of the inductor, you need to know the input voltage out, and which is not a robust solution. There are other techniques also, when you go to that architecture we will discuss. So, and it can also be shown, even if you take the exact current ripple, it may not be good for first scale or the stability point of view. So, what will be the right choice of the slope, that we will discuss when you go to stability and other aspect of digital current mode control. So, only thing we keep in mind that it is possible to implement a fully digital current mode control with ripple emulation, in which the ADC of the current as well as the voltage can be sampled once per cycle. As a result, both the ADC can become a single ADC with two analog mux, that means two analog channel. So, you can time multiplex, and this can cut down the cost because only one ADC, there is no DAC requirement. And in fact, this method also help. Suppose if you take the sample, suppose I am talking about the inductor current like this. Now, when you go for sense current, sometime high frequency, there can be some kind of spike here. For a very high frequency current sensor, there can be spike. But if you take the current sample, for example, you take the clean current sample here when before switch turns off. So, these are the clean sample, right? If you take such clean sample which is actually going, that is, these are my clean samples. These are my clean samples. Then you can add ramp. So, that means as if you are adding ramp here. So, by that way you can actually make the current controller or current loop insensitive to switching noise, and that is not avoidable in analog control. As a result, most of the analog control, even for this case also, sometimes they use a minimum dead time, because if there is a large spike in the current, particularly during transient or some spike, so we need to avoid. And this for buck converter it is easy, but suppose if you are talking about a converter where both side of the inductor has a switch node, or suppose if we take a buck converter, if we place a current resistance across the inductor, then you will not have such issue, maybe very less. But suppose you are talking about a current sense resistance or maybe RDS of the switch. When you talk about the RDS of the switch, this resistance is kept in the switching path. As a result, when there will be turn on and off, there will be LDIDT action. So, naturally such can actually create some spike in the current, and this spike can cause false triggering. That means switch can be turned off at the very beginning, and that may lead to a lot of nonlinear phenomena. So, in analog control, people use something kind of blanking, that means they do not take any action for certain on time duration, then only they compare, and that actually limit the effective duty ratio operation. That means, you cannot achieve a very low duty ratio operation due to this blanking mechanism. So, that means duty ratio below 10% or 5%, it will be 0. So, it will start from 5% to that full swing. But when you go to digital control, such a problem can be avoided because you take the clean sample and you emulate the current slope internally. So, if we compare the performance, naturally this may be faster because the current loop in analog, and you can do lot of trajectory based control. This may be slightly slower, but if you can properly emulate this current emulator, and if you synthesize the trajectory. So, this is kind of a research problem which we are not discussing too much, but I can say that you may not get exact performance in general, but there can be a way to actually anticipate, and you can get a very fast transient current signal. So, performance point of view, as it is in general, without talking too much about the trajectory shaping, this technique is slightly faster because of the analog current loop, but it also requires a D2A converter as well as the analog current analog comparator. And if you go to fully digital with ripple emulation, then you can use 1 ADC, you can avoid DAC, as well as there is no analog comparator, it is a digital comparator which will be much faster with low power, because it is just a CMOS transistor. If you talk about cost, so you can cut down the cost in this technique, but this technique will also impose challenge because the resolution of this emulated RAM will create a duty ratio limit which is not there in analog control, because analog control, it is just a analog signal, there is no resolution problem. The resolution will only come due to the resolution of this ADC as well as DAC. So, it will only give a resolution of the peak current difference, and that will impose some duty ratio resolution. But in this case, the resolution limit will come due to the ADC as well as a resolution of this ripple emulator, which will also, so it is something similar to voltage mode control resolution problem, but you still have a current sample information. So, which will be faster than voltage mode. So, that means cost point of view, this may be effective, but this may lead to even stability problem. So, we need to discuss about their performance and cost trade off, but at this point I will say both are equally good, but this techniques is often used in commercial product. Okay, so, this is about, we discussed the basic concept of digitization, but in the subsequent week we will elaborate detail about the internal architecture, how to develop MATLAB models, then how to simulate it, and effectively we will go for hardware implementation. So, in the hardware we are not going to consider fully digital, because our hardware will have 1 ADC, 1 DAC, but we will show the mixed signal current mode in the hardware architecture. In summary, we have discussed various, we have recapitulated the analog current mode control technique, and this is like a 2 loop control. Then we have discussed how to digitize this 2 loop control, where should we sample, whether we should sample the digitize the voltage or current or their combination. Then we have discussed some issue of sampling and quantization, we have summarized that multi-loop digital control, and we have discussed some aspect of performance and cost, but we will discuss more about this architecture in detail in the subsequent week. So, for today I think we have just summarized the basic steps of digitization. So, that is it for today. Thank you very much.